Hello everybody and welcome to our video on the cross product. So now we're going to talk about another new operation on vectors that we call the cross product. And this one is really going to seem a little bit strange. So let's take a look. If you've got two vectors, A and B, with coordinate components A1, A2, A3, and B1, B2, B3 respectively, then the cross product of A and B is the vector A cross B given by components A2B3 minus A3B2, then A3B1 minus A1B3, and then A1B2 minus A2B1. Okay, so this is a bit of a strange definition for an operation, I think, at least at first glance. So just like with the dot product, we'll see that actually this particular computation has some real geometrical meaning behind it. And so it'll make a lot more sense when we get to that point. But this formula would be really hard to remember. And especially if you are taking linear algebra or are going to take some linear algebra related courses, there's a way in the language of linear algebra we can express this idea of this cross product. That's a lot easier to remember, in my opinion. So first we're going to have to define what a determinant is, and we're not going to do it in the general way. We're just going to talk about determinants of order 2 and order 3, because that's all we will really deal with in this course. So for a determinant of order 2 of a matrix like this, we get A times B, or times D, minus B times C. And the way to visualize this is sort of like you multiply on the diagonals and subtract the two results. So, as an example, for this matrix over here, we multiply 2 times 3, and then subtract the negative 2 times 1, we get 6 plus 2, which is 8. So that would be the determinant of this matrix. Now, what about a determinant of order 3? Now, this one's a little weirder. So the way we take a determinant of order 3 is we take a component, say A1, and then we multiply it by the determinant of the 4 terms that are not in the same column and row as A1. So A1 times this determinant, B2, B3, C2, C3. And then we subtract, and we go to A2, and we multiply it by the determinant B1, B3, B1, B3, C1, C3. So again, by the determinant of the entrants here that are not in the same row and column as A2. And then we add A3 times the determinant of these other entries again. So in this case, B1, B2, C1, C2. So let's just do a quick example of that. So we want the determinant of this matrix here. So we got 2 times. So I'm going to kind of like sketch out as I go. So 2 times this determinant, 0, 1, 5, 2, minus 1 times 3, 1, negative 1, 2's determinant. And then plus negative 1 times the determinant 3, 0, negative 1, 5 here. So we get 2 times the determinant here, which we do with just our little diagonal multiplication and subtraction routine. 0 times 2 minus 1 times 5. Minus 1 times this determinant, which is 3 times 2, minus 1 times negative 1, minus 1 times 3 times 5, minus 0 times negative 1. Okay, so this becomes 0 minus 5, so 2 times negative 5 is negative 10, minus 6 plus 1, so that's minus 7, minus, and here we've got 15. So altogether, this is minus 32. So it's sort of my view that the determinant is best thought of as a notation to describe some algebraic operations that happen to just come up a lot. And they come up enough that creating a notation for them to create a shorthand just made a lot of sense. And so we're going to see real quick that this determinant is an example of that. Or this cross product, I should say, is an example of that. So notice that the result of this cross product is what you get if you were to take I times the determinant A2, A3, B2, B3 minus J times the determinant A1, A3, B1, B3 plus K times the determinant A1, A2, B1, B2. But this is exactly the determinant of this matrix. All right, based on our definition for the determinant of order 3 here. So here, A1, A2, and A3 just happen to be I, J, and K. And our second row and third row are A1, A2, A3, and B1, B2, B3. So again, basically what we're saying here is this is determinant notation is just giving us a shorthand to describe some sort of product and some combinations that pop up naturally in problems and would otherwise be pretty cumbersome to write in general. So A cross B is this determinant. And now what that looks like is the following picture here, right? This cross product is actually the vector that's perpendicular to these two vectors A and B. And we're going to talk more about that momentarily. So for now, just keep in mind that this cross product actually describes a specific vector that happens to be perpendicular to both A and B. So let's just do an example first, just to kind of get the gears moving and take the cross product of A and B here. So first we'll set up our determinant, I, J, K, and lay out our first vector, 1, 1, negative 1, and 2, 4, 6. This gives me I times the determinant of these 4. So that would be 1, negative 1, 4, and 6, minus J times the determinant with terms 1, 2, negative 1, and 6 here, plus K times the determinant from these 4 terms, 1, 1, 2, and 4. Okay, so if we multiply along our diagonals here, we get 1 times 6. Then we need to subtract negative 1 times 4 minus J times 1 times 6 minus negative 1 times 2 plus K times 1 times 4 minus 1 times 2. Okay, so what do we have here? This is 6 plus 4, that's 10. I'm going to rewrite this as 10I. Here we've got 6 plus 2, that's 8. So this is going to be negative 8J. And this here is going to be 4 minus 2. That's 2. So this is plus 2k. All right, well, I think it's about time that we see what this cross product is all about. And this theorem is one of the key facts that tells us something important about the cross product. So the vector A cross B is orthogonal to both A and B. So I said that before, but let's actually prove this. So A cross B, as we've seen, gives us this algebraic expression, right? A2B3 minus A3B2, A3B1 minus A1B3, A1B2 minus A2B1. So if I take the dot product with A, I'm just going to be multiplying each of these components by A1, A2, and A3 respectively. So when I do that, well, let's just take a look here. A1, A2, B3. A1, A2, B3, but negative, so these cancel. And here we get A1, A3, B2, but this is negative. This is A3, A1, B2, but positive. Those are the same thing, right? We can multiply in any order. And likewise, these terms cancel as well. So we end up with 0. And we know that if the dot product between two vectors is 0, that tells us that they are orthogonal. Okay, so let's look at another theorem. Now this one's a little bit more involved on the proof. If theta is the angle between A and B, where theta is between 0 and pi, then the magnitude of the cross product of A and B is equal to the magnitude of A times the magnitude of B times sine of theta. So you can kind of think of this as an analog to our dot product theorem that we were using in the previous section. And again, this shows you that this cross product is describing something important geometrically. We saw that it's describing a vector orthogonal to A and B, and we also see that the relationship of this cross product can tell us what the angle between A and B is. Okay, so what can we do with this information? First, how can we prove it? Okay, well, the cross product's magnitude squared is going to give us the dot product of the cross products. So we're just dotting the cross product with itself, which means we're multiplying each component term by itself and adding them together. Now, really, I'm not going to go into all of the detail of this. You can take a closer look at this in the notes here if you want. But basically, the idea of this proof is we multiply all this out, and we get this big, messy string here of values. And then we want to factor them into this. And this factorization is practically impossible, right? I would never expect a student to be able to memorize or come up with this factorization off the top of their head. But if you want to see that it is true, that's not hard to do. You can multiply these terms out and see that you get the same thing you had in the step before it. So these two expressions are definitely equal. Now, once you take a look at this factorization here, you see that this is the magnitude of A squared times the magnitude of B squared minus the dot product of A and B squared, which is what we've written here. And we already know that the dot product can be rewritten as the magnitude of A times B times cosine of theta. So the dot product squared is just all of that squared. So we can substitute that in place. And here we can factor out A and B, the magnitude of A and B squared from both terms. We get the magnitude of A squared times the magnitude of B squared times 1 minus cosine squared of theta. And the Pythagorean identity for trigonometry tells us that 1 minus cosine squared of theta is sine squared of theta. So altogether, we've shown that the cross product squared, its magnitude squared, is the magnitude of A squared times the magnitude of B squared times sine squared of theta. Now, since theta is between 0 and pi, that means sine is going to be positive here, so we can take the square root of this squared function with no problem and get a positive number. And that gives us our result. The magnitude of A cross B equals the magnitude of A times the magnitude of b times sine of theta. Okay, so that was a little bit of a mess, algebraically speaking, but it's not a complicated proof. It's actually relatively simple conceptually. There's nothing really fancy. It's just computation, but the computation's a little messy. Okay, so in conclusion, as we saw here, the vector A cross B is the vector which is perpendicular to both A and B and oriented by the right-hand rule, whose length is the magnitude of A times the magnitude of B times sine of theta. Okay, so corollary. Two non-zero vectors A and B are parallel if and only if A cross B is equal to 0. Well, that should make sense here, right? Because if A cross B has magnitude 0, then this right-hand side has to be 0. And sine of theta is 0 when theta is 0. So if the angle between them is 0, then those vectors are traveling in the same direction. And hence they're parallel. There's another fact that comes out of the cross product. The length of the cross product is equal to the area of the parallelogram determined by A and B. So this is actually a fairly immediate result because A cross B's magnitude is equal to the magnitude of A times the magnitude of B times sine of theta. But sine of B, the magnitude of B times sine of theta here is the height of this parallelogram. So if that's the height of the parallelogram, right, and that's just comes from sine of theta is opposite over hypotenuse. So the height is just going to be the magnitude of this times sine of theta. And the width of our parallelogram is going to be the magnitude of A. So this is just width times height. Nothing crazy there. Okay, so again, this is another example of something where just this cross product that seems like a really odd operation that we've defined actually gives us some really specific geometric information that relates these vectors together and relates them to constructions you can build with them, right? If you take two vectors, you can define a parallelogram between those two vectors, and the cross product will tell you the area of that parallelogram, or at least the magnitude of that cross product will. Okay, so for our next example, let's find a non-zero vector that's orthogonal to the plane through the points P, Q, and R. And B, find the area of the triangle PQR. So if we want a non-zero vector orthogonal to the plane through the points P, Q, and R, we should think about what that means, right? So if you have P, Q, and R, and they're all in a plane together, which of course you can define a plane by any 3 points. So you've got 3 points, they define a plane, and you want a vector that's orthogonal to that plane. So you think of it like this vector's going up here, makes a right angle with the plane. Well, how would I do that? Well, I would just do that by first identifying two vectors, a vector from P to Q and a vector from P to R. And then when I take the cross product of those vectors, I know that the resulting vector from that cross product will be orthogonal. So let's figure out what those vectors are in the first place. So the vector PQ, we're going to subtract our components, starting with Q, our terminal point minus our initial point, and that's going to give us 4 minus 0, which is 4. 2 minus 0, which is 2, and 0 minus negative 3, which is positive 3. And then our vector PR, that's going to be 3 minus 0, which is 3. 3 minus 0 again, which is 3, and 1 minus negative 3, which is 4. So now we want to take the cross product of these vectors. So we'll just set up our determinant, ijk. So PQ is going to be 4, 2, 3. And PR is going to be 3, 3, 4. This gives us, so I'll write this, the determinant of 2, 3, 3, 4, I minus the determinant of 4, 3, 3, 4, J plus the determinant 4, 3, 2, 3, K. Now I'll tell you, it's a good idea to double check when you're writing these out because it's really easy to just mix up a column or something. So save yourself a little bit of hassle and go back and check those. Like there I wrote a J instead of an I for some reason. Don't know what that was about. So if this is I, then these four are what we want. 2, 3, 3, 4, good. Minus J, all right, and this determinant. So we should have 4, 3, and 3 and 4, that's good. Plus, and we've got our K times this determinant. Should be 4, 3, 2, 3. Yeah, that's correct. Okay, great. Good start. Okay, so 2 times 4 here, that's 2 times 4 minus 3 times 3, I, minus this determinant, that's 4 times 4, minus 3 times 3, J, plus 4 times 3 minus 3 times 2, K. Okay, this is 8 minus 9, that's negative I. And this is 16 minus 9, that's 7, so minus 7J. This is 12 minus 6, so that's 6K. Okay, so that's our new vector orthogonal to the plane through the points P, Q, and R. Now, what is the area of the triangle PQR? Well, it's the same as 1/2 of the area of this parallelogram, right? So if we think about that, this triangle is going to give us 1/2 of a parallelogram. And the area of that parallelogram is equal to the magnitude of the cross product. So the area of our triangle should be 1/2 the magnitude of our cross product. So that's 1/2 the square root of -1 squared plus -7 squared plus 6 squared. It's 1 plus 49 plus 36. That's 50 plus 36 is 86. Let's see, is 86, that's not divisible by 4. So, yeah, I don't really think we can simplify that any, at least not meaningfully. So we'll just leave that in that form. Okay, so that's the area of our triangle there. And that's the end of example 4. So let's go ahead and move on. Okay, so now we're going to talk about those standard basis vectors I, J, and K again. So we know the angle between each of these basis vectors is pi over 2. And so if we apply those earlier theorems from the section, we know like I cross J has to be equal to the magnitudes of I and J multiplied times each other times sine of pi over 2, which is 1, right? So just using that process and also calculating, we could also calculate these by hand if we wanted. But what would we see, right? So we're not going to actually write out all these computations. It would be way too time consuming. But if we did those computations, we'd see the following. A cross J equals K. J cross K equals I. K cross I equals J. J cross I equals negative K. K cross J equals negative I. And I cross K equals negative J. So this actually tells you something really important here. So if you were to do these computations, what you see is that the cross product is not commutative. I cross j is k, and j cross I is negative k, right? So let's think about what I and j are, right? So I is the vector that's pointed in the x-axis. And j is the vector that's pointed towards the y-axis. And k is this vector. So when you cross I first, then j, what do you get? You get k. But if you do j cross I first, you get negative k, right? So you get the vector down here. Now, if you think about that right-hand rule, so when we talk about the right-hand rule, the way we read that with cross products is your starting vector, the first vector, you think of putting your wrist or your arm lined up on that vector, and your pointer finger points towards your second vector here. So you'd have to kind of have your arm twisted around a little bit here. Yeah, so you got to imagine your arm kind of being turned around. It's a little awkward. But your arm's pointed this way, your finger's pointing in the direction of J, your thumb's going to be up and point towards K. But if you were to reverse that order, right, then what ends up happening is your arm is going to have to turn the other way around, and so your thumb's going to be pointed towards negative K. That's basically the heart of the issue, is that your direction of the cross product depends on the order that you take the cross product in. So just be careful about making assumptions that you can, multiply these things in any order, because you can't. Not with the cross product, at least. Now, another thing to point out is that the cross product is not associative. So notice if you take I cross the result of I cross J, well, I cross J is K, so I cross K is negative J. But if you were to first cross I with itself, you would get 0. And so 0 cross J is just 0. So you definitely don't get the same result at all, because the cross product is not associative at all. Okay, so just keep those things in mind. You really have to pay close attention to the order that you take cross products in. All right, let's move on to a theorem. And I'm not really going to prove any of these, but these are the kinds of questions that I might ask a student to prove that I think are pretty reasonable for a student to prove themselves, because all you really need to do here is actually calculate the computations directly, right? So, just give, say, A name, A1, A2, A3, B, B1, B2, B3, and C, C1, C2, and C3. And what you'll see when you run these computations for each side of each equation, you'll always end up getting the same exact thing. So, pretty easy to prove. I would find it a totally reasonable question to ask a student to prove one of these identities here. So the first identity is that if you take the cross product of A and B, that it's the opposite, the negative of the cross product of B and A. And we talked about that in regards to what we call the right-hand rule. So for 2, if I have a constant times the vector A, and then I cross that with B, it would be the same thing if I crossed A and B first and then multiplied by the constant A, or if I multiplied the constant by V and then did the cross product. Now, the cross product is distributive across a sum of vectors, but you have to make sure that you maintain the order of the cross product, A cross B plus A cross C. And same thing if you have your sum first, A plus B cross C, it's A cross C plus B cross C. But again, you have to make sure these cross product orders don't change. That'll mess you up. Now, if you take the dot product of A with the cross product of B and C, that is actually equal to the cross product of A and B with the dot product of C. And finally here, A cross B cross C is equal to A dot product C times B minus dot product B times C. All right, so this one would be one I really would like a student to work out and try on their own and see how that works out. That one in particular is a good one to reinforce. Okay, so we're going to define one more thing here, the triple product, or the scalar triple product of the vectors A, B, and C. So this is actually the thing that we saw here in this property 5 up here. So A dot B cross C. And if you compute this out, you'll see that you get the same thing as the determinant A1, A2, A3, B1, B2, B3, C1, C2, C3. So this is how we usually think of, at least how I usually think of doing a scalar triple product, is the determinant of these 3 vectors in these rows. So this theorem says that the volume of the parallelepiped determined by the vectors A, B, and C is the magnitude of their scalar triple product. So, in other words, if you know the vectors A, B, and C that generate this parallelogram that you're looking at, then you can calculate the volume of this thing directly by just taking this scalar triple product. So, why is that true? Well, the area of the base of this parallelepiped, that's always a tongue twister, is the magnitude of the cross product of B and C, which we saw earlier. The height, h, is just the magnitude of A times cosine of theta. That's just a little trigonometry here, where this is theta. You get a right triangle, and you get that this height, h, is the magnitude of A times cosine of theta. And so if you multiply that by your cross product, our theorem gives us that this magnitude of B cross C times the magnitude of A times cosine of theta is the magnitude of A dotted with B cross C. That's just that dot product theorem from before. And that's the volume, right? So what else do we know? If V is found to be 0, so if the volume of this parallelepiped is found to be 0, then A, B, and C must all be in the same plane. So let's look at this example. Determine whether the points A, B, C, and D are coplanar. Well, first we'll need some vectors to work from. So A, B, we'll get by subtracting the points from B, the components from B, and subtracting the components of A. 3 minus 1 is 2. Negative 1 minus 3 is negative 4. 6 minus 2 is 4. And now we'll look at the ray from A to C. Okay, so our vector from A to C is going to be 5 minus 1, that's 4. 2 minus 3, that's negative 1. And 0 minus 2, that's negative 2. And then we'll look at the vector AD here. 3 minus 1 is 2. 6 minus 3 is 3. And negative 4 minus 2 is negative 6. Now, since I have all of these in vector form, if I want to take the scalar triple product of these things, this thing here, it's really AB dot AC cross AD, but we can just express this as the determinant of these 3 vectors. 2, negative 4, 4, over 4, negative 1, negative 2, and 2, 3, negative 6. So again, another example where just because the way these computations work out, the determinant notation just saves you a lot of hassle in terms of how to think about some of these computations. So this gives us 2 times the determinant of these 4 terms, negative 1, negative 2, 3, negative 6, minus negative 4, times the magnitude of 4, 2, negative 2, negative 6, plus 4 times the determinant of these four terms, 4, negative 1, 2, and 3. And again, I'm going to double check these real quick. Make sure I didn't write one down wrong. Okay, looks good. So this is 2 times negative 1 times negative 6 minus negative 2 times 3 minus a negative 4, so that's a positive 4. And then 4 times negative 6 minus negative 2 times 2 plus 4 times 3 minus negative 1 times 2. This is 2 times 6 plus 6, so that's 12, plus 4 times, okay, so this is negative 24 plus 4, so that's negative 20, plus 4 times, this is 12 plus 2, so that's 14. Okay, so 4 times negative 20 is negative 80, and here we've got 2 times 12 is 24, and this is, let's see, 40 plus 16, so 56. So those add up to 80, and that's negative 80, so altogether this is 0. So yes, they are coplanar. Okay, so that's it for example 5. Let's move on here to another definition. Torque. So, torque is generally something we think of as a physics-focused concept, but our results about torque come directly from this idea of cross product, or at least relate directly to the cross product. So consider a force F acting on a rigid body at a point determined by a position vector r. The torque, tau, relative to the origin, is defined as the cross product of the position and force vectors. Tau equals the vector r cross the force vector, which I didn't put the arrow here, but in context, this has got to be a vector. Okay, so torque measures the tendency of the body to rotate about the origin. The direction of the torque vector indicates the axis of rotation in accordance with the right-hand rule. And the magnitude of the torque is equal to the magnitude of the cross product of r and f, which tells us that the magnitude of the torque is equal to the magnitude of r times the magnitude of f times sine of theta. So in the context of this problem, what this direction says, so let's read this problem first. A wrench 30 centimeters long lies along the positive y-axis and grips a bolt at the origin. A force is applied in the direction 0, 3, negative 4 at the end of the wrench. Find the magnitude of the force needed to supply 100 Newton meters of torque to the bolt. So in other words, what this says here, the direction of the torque vector indicates the axis of rotation. So it's essentially telling you, if the torque is pointed either, in the positive or negative direction, and you're, say, turning a bolt, it's telling you if you're putting the bolt in or taking the bolt out, right? Now, if we take a look, let's try to draw this picture terribly, as I usually do. So we've got a wrench. I think that's a pretty okay wrench. I'd write like Craftsman on here or something, but copyright and all that stuff. So who wants to deal with that? Okay, so a force is applied on the end of this wrench, and the force has a 0 in the direction of x. So the direction sort of coming out of the screen towards the person. It's a 3 in the direction of y and a negative 4. So it's basically something like this. call this F. Now, there's also a direction vector here. And so the direction vector is just pointed towards the y-axis in the way we've set this picture up. So, well, it specifies along the positive y-axis. So 30 centimeters is 0.3 meters. So that means we're going 0.30 for our direction vector. Okay, so if we want to find the magnitude of the force needed to supply 100 Newton meters of torque to the bolt, well, what do we need? Well, first of all, I should say I actually should not have written that this is the force vector. I should have said that this is the unit vector for the force, right? Or actually, it's not even the unit vector. It's just a vector in that direction. So I can't even say that. Let's just call this like we'll call it little f vector, and then we'll figure out what the magnitude needs to be momentarily. Okay, that's the direction that we're headed. What we need is the magnitude of the force. So what we can find out first is the angle between these vectors. It looks like that's what we're going to have to do. So let's find the angle between these vectors. And we can actually do that by just using the cross product. Or we could use the dot product. So there's a bunch of different ways we could do that. So actually, in this case, I want to use the dot product because we're going to end up just using the shortcut for the cross product part of the thing. So let's just practice the dot product a little. So r dot at little f here, going to give us 0 times 0 plus 0.3 times 3 plus 0 times -4. This gives us 0.9, and the other terms are 0, so those cancel. And we know that the dot product of these two things should be equal to the magnitude of each one times cosine of theta. Now the magnitude for the r vector is simple because it's only going in the y direction, so it's going to just work out to 0.3. For this one, we'll take the square root of 0 squared plus 3 squared plus -4 squared. So what do we get here? 0.9 divided by 0.3 should just give us 3, right? So this gives us 3 divided by this square root, which is the square root of 25, which is 5. Equals cosine of theta. So theta equals cosine inverse of 3/5. So this is 53 degrees, but actually, it doesn't matter. We can do this in degrees, 53.1 degrees. Now, if we want a total of 100 pounds of torque, 100, not pounds, 100 Newton meters, wrong unit. If we want 100 Newton meters of torque, that should be equal to the magnitude of r times the magnitude of f times sine of 53.1 degrees. And what we're trying to solve for here is the magnitude of the force. So we're going to just divide 100 by the magnitude of r times sine of 53.1 degrees, and that's going to give us the magnitude of f. Now, the magnitude of R we already know was 0.3, so we just plug this all into a calculator. And I got that this magnitude should be 416.8 newtons, roughly. Hopefully I didn't plug anything wrong there, but if I did, accidents happen. All right, well, that's it for this one, so thank you for watching. Have a good day.